Hello, this is Chuck Ridgway, Automation Technology Manager from Horner. Thanks for joining us for another Tuesday live stream. Today is part 4 in our 4-part series on the IEC 61131 programming languages in Cscape. Today we're going to cover Sequential Function Chart, which is the 4th of the 5 languages that we're covering in this series. Now, as I've mentioned here earlier in this series, IEC 61131 is something we really should cover more here on this channel, especially since Cscape does it really well. I've really enjoyed the last 4 weeks in exploring these languages with you, so if you haven't checked out the other parts of the series, I would highly encourage that. So let's take a look at how we're going to break down today part 4, Sequential Function Chart. As always, we're going to start with a really quick review of IEC 61131 and how to enable it in Cscape, but we're quickly going to transition to all about Sequential Function Chart. What is it? How is it useful? How is it constructed? And as always in this particular series, we're going to spend plenty of time doing demonstrations. I went ahead and pre-recorded one for you this morning, and then I have a second one I'll be going through for you completely live. Let's go ahead and get started. IEC 61131 is the IEC standard for the implementation of PLCs. Now, it consists of 5 languages, and in this series, we've covered ladder, structured text, function block diagram, and today, sequential function chart. We haven't covered instruction list. I think it's a language that's kind of been relegated to second-tier status. It's kind of like an assembly language type approach, and we're not going to cover it in this series, but it is still supported. Here at Horner, we talk about standard IEC capabilities and enhanced IEC capabilities. The enhanced IEC capabilities we've covered in this series, and they're listed there on this screen. Meanwhile, rest assured that everything I'm showing you during the series is available with standard IEC. If you want to utilize IEC programming in Cscape, you need to enable it first. So from Tools, Application Settings, you'll need to check the appropriate box so that when you do a File New to create a new program, IEC 61131 languages will be an option. Now let's get to today's topic. What is Sequential Function Chart? So Sequential Function Chart is another graphical language as part of the IEC 61131. If you'll remember, both ladder logic and function block diagram are also graphical languages. Sequential function chart is drawn like a flow chart, unlike ladder, which is more like a line drawing, an electrical line drawing, or unlike function block diagram, which is more like a schematic. And remember, structured text as well as instruction lists, which we didn't really cover, those are textual languages. So SFC is drawn like a flow chart. How is SFC useful? Well, it is a great tool if you're going to be programming sequential operations on a machine. Also, it's great in those scenarios where you've got multiple states of operation and you want to be able to keep them straight. And it really can help an engineer break down large and complex processes into smaller, easier to understand pieces. So it absolutely has some function that you should be aware of. How is Sequential Function Chart constructed? Because it's not necessarily a language that gets covered, say, in school or gets covered through learning just ladder logic in an industrial setting, there's a little bit to it that you need to study. So basically, the first thing to talk about with SFC are steps. What is a step? Well, a step is a stable state, and it's represented on the drawing or in the graphical language by a square box. And on the right there, you'll see a square box with a 1 inside and another one with a 2 inside. And those are basically states or steps, if you will. The one that has double lines around it, number 1 on the right there, that is an initial state. And with an initial step or initial state drawn in double lines, it represents the situation when the program is started. So if you need to initialize any variables or anything like that, you're going to do that in the initial step. Now for regular steps as well as the initial step, they have actions. And there's 3 we're going to talk about. You've got the P1 action as labeled in Cscape. That's the action that's executed once when the step first goes active. Then you have the P0 step or action, P0 action, which is executed once when the step goes inactive. And then you've got the N action, which is executed always when the step is active. How do you program these steps, or what language do you program these actions in? You use the other IEC programming languages. So to program the logic within the action within a step, you might use structured text, which is kind of the default language, but you could also use ladder diagram, function block diagram, or even instruction list. Now, to get from step to step requires a transition. What is a transition? Well, a transition represents a condition that changes the program activity from one step to another. And each transition is completed with a Boolean condition that must be true. So if the Boolean condition that you've designated as your transition, if it becomes true, then that transition can be crossed and you'll move on to the next step. Now there's something called a timed transition, which basically passes through, which basically you can pass through after an elapsed time from the previous step. So if you're going to execute a step for a certain number of seconds, for instance, and then move on to the next step, you're going to use a timed transition. What are the form of transitions? How do you specify those? Well, they can be a simple expression in structured text. They can be a single rung and ladder. They can even be just a variable that becomes true. So they're pretty simple to configure. Another couple things we should talk about, and that is starting with divergences. So what are divergences? Sometimes called alternate steps or alternate paths. So basically, divergences are alternative steps for the program to execute, and they're listed in left to right priority order, and they're drawn using a horizontal line connecting them. And divergences always start and end with transitions. So with a divergence, if we take a look at that first diagram at the top right there, one of those two paths is going to be executed. One of those two parallel paths is going to be executed. If the condition leading into, or the transition leading into step 101 is true, then you're going to execute 101 because it has priority. But if that is not true, and the condition leading into step 102 is true, then that parallel path will be executed instead. And then you have parallel branches. Those are a little different because basically those represents parallel paths which are both executed. It's not one or the other, they're both executed simultaneously. And those are drawn using double lines to differentiate them from divergences. And unlike divergences, parallel branches always start and end with steps. So that's a little bit about the construction of SFC. Now let's just dive right into demonstrating. I've got two demos for you today. The first one I pre-recorded this morning, and I'm going to show you in that demo precisely how to build really from the ground up an SFC logic chart. And in that first example, we're going to do some really simplified paint mixing. We're effectively going to stir a solvent. We're going to add one of two pigments, either red or blue, and then we're going to shake up the paint and we're going to be done. So obviously very simplified example, but it shows step by step how to create an SFC from scratch. So because I pre-recorded that this morning, let's go ahead and I'll go ahead and show that to you now. Let's go ahead and program up our simple paint mixer application in SFC. Now, before you came on board here with this demo, I've already created my variables. I've also already drawn a control and status screen where I can select either red or blue paint, press the start button, and then stand by and watch as my actuators turn on and off as we move through the process. So let's get started in programming this SFC routine. I start up here under Logic Modules, Main Loop Modules, right-click, New Logic Block, and I'm going to select SFC here. It automatically drops an initial state in there for me. Initial states are typically where you would configure the default states for your actuators or any other conditions that you want to occur when you start running this particular routine. So for now, we'll come back to this later, but for now I'm just going to label this as init. All right, I'm not going to do anything else but I'll label it as init. We'll come back and do any initialization later. Anytime I edit one of these secondary editors, it's going to ask me if I want to keep my changes. I'm basically going to say yes if I don't screw anything up. Okay, next we're going to have a transition. So I move to the box that I want to add the transition, select transition, and the transition out of the initialization state is really just, the condition at least, is just for my start push button to be pressed. When that's pressed, I want to move out of the initialization state and I'm going to go into another state. And this first state is where I'm going to turn on my stirrer. So I double click here. I'll label this as stirrer control. And then when I first enter into this state, that's P1, I'm going to turn on my stirrer. So stirrer equals true. Now, that's all I'm going to do in this state. I'm going to turn on my stirrer and leave it on. So I'm not going to configure anything for any of these other actions. So I'm done with the stirrer state for now. The next transition I want is, this is where I choose between red paint or blue paint. So I need a divergence here. So I highlight where I want the divergence to start. I press this button. I highlight where I want the divergence to end. I press that button. Now keep in mind, divergences are a choice between multiple alternate paths, and they always start with transitions. So I'm going to add a transition here and a transition here. So this will be the transition that says, hey, do you want to make red paint? And we'll go in this one. If red select, we'll go down here and make sure I'm getting the right name here. Red select, yeah, if red select is on, that transition, or that condition I should say, over here we have blue select. So those are the transitions into our next states. What is the next state? Well, we're going to turn on our red valve. So right when we first go in, so that's P1, we're going to turn red valve equal true. Now, when we leave this state, we're going to turn our red valve false. So we've done that. And then when we're making red paint, we need to leave that red valve on for 7 seconds, let's say. So I've configured another transition and I'm going to change it to a timed transition, which is in milliseconds. So 7 seconds is 7,000. Now I'm going to do something similar for the blue paint, except it only needs, that blue valve only needs to be on for 5 seconds, let's say. So I highlight here, configure or add the state. This is my blue paint. When I first go in here, blue valve equals true. After I leave, blue valve equals false. Just like this paint, I'm going to have a transition, and then I'm going to turn it into a time transition, and this time it's only 5 seconds. Now I need another convergence here, because the rest of my steps are the same. So I'll program the back side of the convergence and the front side of the convergence, and then the next stage, or the next step, is going to be where I'm going to turn on my shaker. But before I turn on my shaker, when I first, well, let's go label it as shaker. When I first go in, my action is to turn off my stirrer and then turn on my shaker. And then when I leave this state, I'm going to turn off my shaker. So that should be everything I need to do for that guy. And then all that's left is how long do I want to shake if this is a time-based transition. So I highlight there, hit transition, highlight it again, convert it to a timed one, and let's say that we just have 10 seconds of shaking. And then our last state is done. So in this state, when we first go in here, okay, so we'll just call this process complete. And when we first go in here, we're going to turn on our ready LED. And we'll leave that on for 5 seconds. So another transition, convert it to timed. And oops, there we go, convert it to timed. And then we'll leave that on for 5 seconds. That light, ready complete light on for 5 seconds. And then I did a little out of order, but there's also a jump here at the end because when I'm done, I want to jump back to number 1. Step number 1, which is our initialization state. So that should be, if I didn't have any typos, that should be what we want to accomplish here. Normally in the initialization state, this is where I might go in here and I might set as the action stir equals false, red valve false, blue valve false, etc., etc. I'll skip that here just because it's a little time consuming to watch me type, but that's what you would probably do here in the initialization state. Let's do an error check and see if we have any issues. So I'm going to go here and look at the error check. Hey, everything went good. So I typed it all in properly, it appears. Let's go ahead and download this now. So let's go ahead and bring in our unit here and watch the rest of the download. So it looks like our download is complete. Now let's give it a quick test. So what I'm going to do is I'm going to go ahead and go into debug mode so we can kind of watch things happen on the screen as we also watch the user interface on the bench or the OCS on the bench. All right, so we're starting out in the initialization state. We need to select either red or blue. Now, if I select red, it's going to execute red. If I select blue, it'll execute blue unless red is also selected. Because remember, with a divergence or an alternate path, it's going to have priority from left to right. So if red is selected, it's going to do red, even if blue is also selected. Hopefully that was relatively clear for you. All right, I'm going to go ahead and select blue and then kick things off here. And it immediately turned on my stirrer, turned on the blue valve, moved to the shaker, and after a few seconds, it's going to be ready. Okay, so that's basically what happened. Obviously, this stage right here, this step right here, just was executed long enough to turn that stirrer valve on or stirrer on, and then it jumped right down into selecting to making the paint, if you will. Okay, so this time I'm going to go ahead and press the red button, but both of them are now selected. Oh, notice one thing here. My paint ready button is still on. So I really didn't handle that properly. So let's fix that and then do a download and then be done. So that's where the initialization stage, if it says, for instance, when we're in the initialization stage, if the ready LED, which is the variable name, is set to false, then we don't have to worry about it being on from previous trials. So let's go ahead and add that there. And normally, as I mentioned before, we'd probably set a bunch of other variables off as well just to make sure that they started out in the correct state. So I've made that change. Let's go ahead and download that. Okay, let's go ahead and check this out. I'll go back into debug mode here. Okay, this time what I'm going to do is I'm going to select both red and blue and see what happens when I press start. Okay, it immediately turned on the stirrer, then it moved right to making red paint. Because remember, left to right priority-wise, red has priority. And then after the timeout, it moved to the shaker. And then basically the paint is now, the process is complete. And the paint ready light is now off as it should be. That was our first demonstration. We showed you how to build from scratch SFC logic. So for our next demonstration, I'm not going to go into all the details and build it from scratch. I'm going to show you another project that's similar but a little bit different. Once again, it is following a process or controlling a process. This time, we're doing a basic process of filling a tank, heating and mixing. We have an optional injection of chemicals, and then we're going to drain the tank. But we did a few things differently this time that'll illustrate some of the other capabilities that are available with SFC. So this is one I'm going to just show you live. So let me go ahead and switch to Cscape. And then I'm going to go ahead and bring in my OCS on the bench here. Okay, so with this project, we've done a few things a little bit differently. So let me show that to you. First of all, with this project, I have multiple main loop modules, and they're in different languages. One of the strengths of IEC is the fact that you can do different routines in different languages. Whatever the strength of that language is, you can take advantage of that for that portion of your project. So in this case, because we are doing some analog involving filling as well as temperature control, I had some analog signals to deal with. So I went ahead and took advantage of function block diagram for my signal conditioning. So in this case, for my level monitoring, I took the output from my level sensor, which is an analog input connected to an AI register, moved that into a variable called tank level AI, and then I scaled it to millimeters because presumably the level sensor I'm using scales 4 to 20 milliamps over to 0 to 1,000 millimeters, for instance. So that I did in function block diagram. And then I also did, let me briefly turn off my picture-in-picture here. I also did a conversion, a temperature conversion from 20th degree C increments coming from an RTD sensor, converted to a real value, and then scaled it in real over to single degrees Fahrenheit. So that's what I did here in function block diagram. So it's a good language for doing that sort of signal conditioning. Now, if you take a look at my screen here that's shown on the page, you can see that I have a number of graphical representations of valves and tank levels and those sorts of things. And if I pull up my screen, you can see that several of these objects, they're actually using visibility, the visibility attribute, to turn on and off different objects on the screen. So to take advantage of visibility, I have to create a visibility variable for each of these objects. And that visibility variable is an integer. So that means I need to take some bit type states of on or off and move those over to an integer for the purpose of hiding certain things on the screen or making them appear. So again, I could have chosen any language I wanted to for that, but I decided to use ladder in that case because it was really easy to take the status of a actuator and copy that over to the lower bit of that attribute register that we're using to control the visibility of those objects. So again, I had my choice of all the languages. I went ahead and did it in ladder because it was really simple. Okay, now let's get over to our actual process sequence written in Sequential Function Chart. And you'll see there's a lot of things that are the same. I spent a little more time on my initialization in order to set the initial values of more variables. So that is more complete. I used a little more of the commenting in these as well, because that's always available and a good idea. And then a couple other things that you may notice. We've got our transition that are similar with start cycle. We move to filling a tank. We wait for the tank level to exceed a set point. And then we have 3 parallel tasks here, or 3 parallel steps. Now, unlike our previous example, these are parallel tasks or parallel steps. So they're all executed simultaneously. It's not a one or the other scenario. And you can tell that through the double lines in the convergence and the divergence. So what we have going here is we've got a step for heating the water that's simultaneously with mixing the water, that's simultaneous with injecting chemicals. But keep in mind, in our example, when we inject the chemicals, it's an option for every batch. So there's a button here in the lower left-hand corner that the operator will select as he's making the batch or before he makes the batch that says, hey, I want to inject the chemicals or I don't. Okay, so the logic inside of this stage, inside of this step is a little more complicated. And I also decided to use ladder instead of structured text here. So when we take a look at what happens action-wise when we enter this step, you'll see a simple rung of logic that basically says, if my inject option is on, then I want to go ahead and turn on the injection valve. Now, one thing I haven't told you is that we only want the injection valve to be on for, say, 3 or 4 seconds. We don't want it to be continuously on. So while this state is active, we've added a timer. And basically, we're timing how long the injection valve is on. And once it's on for 3.5 seconds, we turn it off with a reset coil. And then just to be complete, even though it probably isn't really needed, when we exit the state, we're going to go ahead and turn off the injection valve always. So this is a little different than the last example. And then after these states are complete, we move on down here. Once the water temperature exceeds a set point, then we go ahead and we drain the tank. And then once the tank is down below a minimum level, then we call the process complete. Let's go ahead and run through this guy one time. So I'll bring my bench unit back on and I'll go into debug mode. Now you'll notice as soon as I go into debug mode here, it defaults to debugging with one of the other routines. But I'm going to go ahead and head into my process sequence here. And let's go ahead and run through here. Okay, so it starts with a start cycle. And in this example, my start cycle is a switch. So I'll go ahead and kick things off here. So now I'm in the fill mode. You'll notice the fill valve is now on. I'll use this pot on my handy dandy IO simulator to simulate filling up the tank. And when my tank reaches its set point or exceeds 800 millimeters, my fill valve will turn off, and my inject valve is turning on briefly, at least for 3.5 seconds. There it's turned off. Now, when I first entered these parallel states, also you'll notice my mixer turned on as well as my heating element. And so now we're waiting for the heat to go up to temperature. I'll go ahead and use the other pot to simulate my temperature rising, which it did. And now we're left with the drain valve being open. And I'll go ahead and turn this guy down to simulate draining the tank. So we'll run through it one more time quickly, but this time without the injection option. Let me move my temperature down so it doesn't trip things up too soon. All right, kick off the process. Now we're filling. When we reach our set point this time, our inject valve should remain off, which it did. Mixer and heater are on. As soon as we get up to temperature, our drain valve turns on and we can go ahead and drain our tank. Okay, so that is another example of SFC with a slightly different process, this time utilizing ladder logic for the actions on one of the steps. That's one of the beauties of SFC, is you do have your choice of a few languages when you're programming the actions within each step, and you have your choice of ladder or structured text when you're programming transitions. Very good. So hopefully you found those examples valuable and you'll get a chance to start working with SFC for a project or maybe just on the bench to get familiar with it so you'll be ready to use it on that future project. Let's go ahead and wrap up today's topic. Once again, SFC looks like a flowchart, so that's one thing to keep in mind as a key point from today. And it really makes it easy to break down complex processes. And your actions and transitions can be programmed in other languages, which also is convenient. If you prefer structured text, you can use primarily structured text. If you prefer ladder, you can use primarily ladder, or you can do like I did and mix and match to a certain extent. So that's SFC for this week. Now I want to remind you that we're here every week, Tuesday at 2 o'clock. We're always available to answer your questions live if you watch Tuesday at 2. Even if we pre-record the entire video, we always have someone standing by to answer your questions. Also, next week, now that we're done with our IEC series, we're going to go back and we're going to talk about an interesting topic, and that is we're going to talk about the choice you might make to install your OCS outside the control panel on the dory like you normally would, or maybe should you consider mounting it inside the control panel. Our quarter DIN OCS models, the XLE, XLT, and XL4, they come with DIN rail options for mounting, so that makes it an easy option if you do choose to mount your OCS inside the control panel. So we'll talk about the different trade-offs there and what the advantages might be and some hints if you're going to do that. So I do want to remind you that if you haven't done so already, please subscribe to our channel. We're closing in on 1,000 subscribers, which is great since we started from very, very few back when we started this channel a while back. And it's exciting that that number's building up. So again, if you haven't subscribed, go ahead and do it. We won't bother you with access notifications or anything. As you subscribe, if you choose notifications, you'll be notified every time we go live, which is once a week, or every time we post a new video, which you'll probably be interested in anyway. Okay, so that's it for this week and sequential function charts. Next week, we've got another video for you, as I've mentioned. So until then, let's all get out there and do us some good.